Welcome back, everyone. Japan has been at the forefront of research into space-based solar power for decades. The idea is to collect solar energy in orbit, where sunlight is continuous, and then beam that power to Earth in the form of microwaves. Japan's Ministry of Economy, Trade and Industry and the Ministry of Internal Affairs and Communications have both supported this program, often in collaboration with the Japan Aerospace Exploration Agency, known as JAXA. The objective is to secure long-term energy independence for Japan and to demonstrate the technical viability of wireless power transfer on a large scale. To understand how space-based solar power works, we begin with the satellite itself. A satellite equipped with large photovoltaic arrays converts sunlight into direct current electricity. Unlike on Earth, the panels can operate in constant sunlight without the interruptions of day and night or weather. That electricity is then used to power a microwave transmitter. The transmitter converts the direct current into microwave frequency radio waves, typically in the range of 2.45 GHz or 5.8 GHz. These frequencies are chosen because they can pass through the atmosphere efficiently with minimal loss. Once converted, the microwaves are directed toward Earth by means of a phased array antenna. This type of antenna uses many small radiating elements, each controlled with precise timing to steer the microwave beam electronically. By adjusting the phase of the signal at each element, the combined output can be directed with great accuracy. JAXA researchers have demonstrated laboratory models of phased arrays capable of steering microwave beams over large distances. The accuracy of the beam is critical because any misalignment could result in reduced efficiency or safety concerns. On Earth, the incoming microwave beam is received by a rectifying antenna, known as a rectenna. A rectenna is a grid of dipole antennas connected to diodes. The antenna captures the microwave energy, and the diodes convert the alternating signal into direct current electricity. This direct current is then inverted into alternating current and fed into the grid. Rectennas have been tested at scales ranging from a few meters to several kilometers. Mitsubishi Heavy Industries has worked on designing rectennas optimized for efficiency and safety in Japan's field experiments. The principle of wireless power transmission is not new. Back in the 1970s, NASA and the US Department of Energy carried out experiments in Goldstone, California, where they transmitted 30 kilowatts of power over a distance of 1 mile using a microwave beam. Those experiments demonstrated that power transfer efficiencies above 80% could be achieved in controlled conditions. JAXA has built upon those foundations, adapting the technology to modern photovoltaic and microwave components. One of the most significant recent demonstrations came in 2015, when JAXA successfully transmitted 1.8 kilowatts of power wirelessly over 55 meters using a phased array antenna. Researchers published these results in IEEE Spectrum, noting that the system achieved high efficiency in a ground-based setup. Although the power level was small compared to the requirements of a space system, it proved the concept could work with controlled beam steering. Mitsubishi Electric and Kyoto University collaborated in this effort, highlighting the close ties between academic and industrial research in Japan. A key engineering challenge is building solar arrays that are both light enough for launch and large enough to collect significant power. Conventional solar panels used in satellites are just too small for multi-megawatt power levels. Instead, engineers are exploring lightweight, thin film photovoltaic materials that can be rolled out into kilometer-scale arrays. Companies such as Sharp Corporation have developed thin film cells with high efficiency that could be adapted for orbital use. The integration of these panels into deployable structures is an area of ongoing research at universities like the University of Tokyo. Once in orbit, the satellite must maintain precise orientation toward both the Sun and Earth. This requires advanced attitude control systems. Reaction wheels and control moment gyroscopes are commonly used for satellite orientation. For space solar power satellites, these systems must handle continuous operation with high precision. JAXA has partnered with NEC Corporation to test control algorithms capable of keeping a large structure stable while transmitting a microwave beam accurately to a ground rectenna. This is a major departure from conventional satellites, which only need to point antennas at relatively small targets. The safety of microwave transmission is a common question. At the power densities planned, the microwave beam would be spread over a large area, resulting in field strengths lower than those encountered in a household microwave oven. JAXA and the Ministry of Internal Affairs and Communications have set strict safety guidelines. Researchers at Kyoto University published work in Science Advances, analyzing the biological effects of 2.45 GHz microwaves at the intended intensities. Their findings suggest the system can operate safely with proper beam control and fail-safe mechanisms that shut down transmission if alignment is lost. The near-term goal for Japan is to carry out a space demonstration of beaming several kilowatts of power from an orbiting satellite to Earth. This is expected to take place by 2026. The demonstration will validate beam control, rectenna reception, and integration with the grid. Medium-term objectives include scaling up to megawatt-class systems by around 2034. Long-term ambitions involve gigawatt-scale satellites that could supply a substantial fraction of Japan's electricity demand. Each stage presents unique technical hurdles that must be solved sequentially. Comparing this technology with terrestrial renewable energy highlights both advantages and disadvantages. Solar panels on Earth are subject to weather and night cycles, resulting in capacity factors around 20 to 30%. In orbit, panels can achieve capacity factors above 90%. However, terrestrial solar installations are far less expensive and do not require launches into orbit. Researchers at the University of Tokyo have emphasized that the economic feasibility of space solar power depends heavily on reducing launch costs. Companies like SpaceX, through its Falcon 9 and Starship rockets, have set new standards in reusable launch vehicles that Japan's program may leverage. Japan's approach can be compared with China's program at the Chinese Academy of Space Technology. In 2020, China announced plans to test space-based solar power, beaming from low Earth orbit. Both nations are pursuing similar technical paths, but Japan emphasizes international cooperation. JAXA has signed agreements with the European Space Agency to share findings, and papers in journals like Acta Astronautica have detailed collaborative studies. These case studies allow Japan to benchmark its progress against other spacefaring nations, while contributing to global research. One limitation is efficiency. Even if orbital solar arrays collect energy at high capacity, each conversion step reduces total output. Photovoltaic panels convert sunlight to electricity at around 30% efficiency. Microwave conversion may lose another 10%, and atmospheric transmission plus rectenna conversion reduces further. The net efficiency from sunlight to grid electricity may be only 10 to 15%. Researchers at Osaka University have published in Applied Physics letters discussing improvements in diode rectifiers to push efficiencies higher, but these are still in experimental stages. Another challenge is durability. Satellites in geostationary orbit face constant radiation and thermal cycling, which can be pretty harsh. Thin film photovoltaic materials may degrade over time. Maintenance in orbit is difficult, although robotic servicing technologies are being developed. JAXA has partnered with Hitachi to study autonomous robotic arms that could replace or repair modular components of a solar power satellite. These systems would build upon technologies already demonstrated on the International Space Station, but adapted for larger structures. Cost is a central concern. Launching thousands of tons of hardware into orbit remains expensive, even with reusable rockets. Megawatt-class systems could require dozens of launches. Analysts at the International Energy Agency have noted in reports that terrestrial renewables will continue to dominate due to lower cost. However, Japan views space solar power as a strategic investment in energy security. If successful, it could provide stable baseload power without reliance on imported fuels. This makes the program attractive, despite near-term economic disadvantages. Looking at the medium term, integration into Japan's national grid is another area of research. Rectenna sites must be located in open areas with minimal interference. Researchers at Tokyo Institute of Technology have modeled how rectennas could be integrated into rural regions, with output feeding directly into high-voltage transmission lines. These studies were published in IEE Transactions on Microwave Theory and Techniques, emphasizing the need for careful planning of land use and transmission infrastructure. There are also questions of international regulation. The International Telecommunication Union must allocate frequency bands for microwave power transmission. Spectrum allocation is already crowded with communications satellites, radar, and broadcast services. Japan's Ministry of Internal Affairs and Communications has engaged in discussions with international bodies to secure the necessary bandwidth. This regulatory environment will shape the pace at which space solar power can transition from experiments to operational systems. In the long term, researchers envision networks of multiple satellites transmitting power to various rectennas around the world. A global grid powered in part from space could reduce dependence on fossil fuels and provide power to remote regions. Achieving this vision will require breakthroughs in materials, launch systems, and wireless transmission technology. As of 2024, Japan's program remains experimental, but steady progress continues. The planned demonstrations in 2026 will be an important milestone, showing whether decades of research can translate into practical results. In conclusion, Japan's work on space-based solar power beaming represents one of the most ambitious energy projects in the world. It involves satellite photovoltaic arrays, phased array microwave transmitters, and rectennas on Earth. Companies such as Mitsubishi Heavy Industries, Sharp, and NEC are central, alongside universities like Kyoto University, Osaka University, and the University of Tokyo. Government ministries provide support, and JAXA coordinates the overall program. The challenges of efficiency, cost, and regulation remain significant, but the technology is steadily advancing. Demonstrations in the near future will clarify its potential role in Japan's energy landscape. Thank you very much for watching. Please like and subscribe.